Let's continue where we left off. So we started the continuous strategies and duopoly, but we were in the middle of it. So let's start from the start of the slide deck again. Hopefully today we'll finish game theory that we wanted to cover, and then we'll start reinforcement learning, fundamentals of reinforcement learning. So let's see how much we can go. And continuous strategies and duopoly. So continuous strategies, what is that? First, we said that continuous strategies refer to when the action space is continuous, right? So it's kind of related to mixed strategies as well, but in mixed strategies, the actions themselves were discrete, but we're saying that let's perform the actions stochastically, probabilistically, right? So for example, we might say maybe with probability 70%, I'll do this action. With probability 30%, I will do the other action. So this is mixed strategy. But continuous strategy says that when the actions are continuous themselves, such as setting the price is continuous, right? Whether you make it $1, $1.2, $1.9, $2, $3, etc., right? So setting, for example, the price is continuous, right? And as I say, slightly different from mixed strategies in the sense that mixed strategies continuous as an interpolated probability between selection of pure actions, but a continuous strategy has continuous actions itself, right? But by the way, as you know, feel free to interrupt me whenever you want. So, duopoly. This part of the course, I think, is good for, especially for people who work in finance and management sciences. So, duopoly means that two companies are competing in the market, right? Such as Google and Meta, for example, and they are both dominant. Monopoly means that one company dominates the market, such as I said an example. For example, in the search engines, I believe that Google is dominant, although Bing is trying its as hard as it can, Microsoft, but I think still Google is dominant, right? So at least in search engines, Google is monopoly. And three most well-known models of the duopoly are what? Cournot competition, Stackelberg competition, and Bertrand competition. People in management sciences have seen these a lot, and in finance. And each of these names are after the scientists, Cournot, Stackelberg, and Bertrand. These are scientists in that area. And why am I saying this in this slide deck? Because these competitions have continuous strategies. So these, you can see them as examples of games with continuous strategies, okay? So actions in these games or competitions are continuous, right? Okay. So first, let's see Cournot competition. At the end, we'll compare these competitions. So Cournot competition, it was proposed in 1838. As you see, it's a bit old, and it has continuous strategy space, right? And it's a duopoly. So we have two markets competing with each other, right? And two firms or companies choose output levels or quantities in competition with each other. So assume we have two companies, maybe chocolate making companies, chocolate companies, whatever you call it. Assume they are chocolate companies, and they can generate how many chocolates per period of time, right? So that's called output levels or quantities, right? So for companies, we have output levels or quantities, and we denote the quantities by Q, standing for quantity. So as here we have duopoly, we have Q1, Q2. Q1, the number of products of company 1, Q2 number of products of company 2, and QI, I mean I goes from 1 to 2, right? Q1, Q2. So in this competition, what are they competing about? The output levels, the quantities, right? And also they are making simultaneous moves. So simultaneously, each of them makes Q1. So the first one makes Q1 chocolates, the second one makes Q2 chocolates, right? Simultaneously. So one of them doesn't see the action of the other one sooner, right? And as I said, every company makes QI quantities. Actions are choosing quantities Q1 and Q2 simultaneously, of course. So as you see, actions are continuous. Why? Because Q1 and Q2, they can be anything. Although these, when I say continuous, I mean it's not finite, right? So although it's integer here, but I mean there is no finite number of actions, right? So marginal cost per making quantity. Assume whenever we make something in the industry, of course we need some materials, right? So for those materials you have to pay something, right? You have to, nothing is free in this world. So assume marginal cost per making quantity is C, denoted by C. C is standing for cost, and assume it is 12. So what does it mean? For example, 12 cents or $12, whatever, the scale is not important here. 12 cents or $12 per chocolate. This is how much they pay for initial materials of the every chocolate bar, for example. And the demand, or the total generated quantity, of course, the demand equals total generated quantity. Why? Because they generate as much as people want, right? In the in industry. For example, if people want per year, they want 1,000 chocolate bars, so they generate 1,000 chocolate bars, right? Otherwise, if they make more, it will be wasted. So the demand is equivalent to total generated quantity, right? And the demand is the number of products that people want. So we denote it by capital Q, and it is equal to Q1 plus Q2. Why? Because the total quantities that are generated is the summation of the quantities generated by the companies, right? By the way, in parentheses, I'll let you know that I'm not in management. I'm not in management science, and I'm not in finance. So if any of you know more than me, feel free to jump in my conversation and correct me if I make any mistake or if I need to be corrected. Okay, so let me know. So this is a demand and profit per quantity. So of course, no one does anything without any profit in this world, right? So the company wants to have some profit. Profit of Q, so it's a function of Q, the demand, right? So assume it can be a constant, like 120, right? But there are some other things which affect the profit. And what are those? How much they generate. The quantities affect the profit. And why do we have minus behind them? Why? I already explained this in the previous session. Do you remember that? Why? So what does this mean? When I have minus Q1, it means that when I increase Q1, the profit goes down, right? Or Q2 minus Q2, when I increase Q2, profit goes down. In other words, when company 1 generates more chocolates, or company 2 generates more chocolates, or both make more chocolates, the profit goes down, the profits of the companies. Why? You don't need to know science about it, just your intuition. When you have when you have a lot of product in the market, then the price of that product goes down, right? I told you an example. I said, for example, compare Apple and Samsung. I'm talking about phones. For example, my phone is Samsung, it's cheaper. Apple is more expensive. Why is Apple more expensive? Apple has less number of phones in the world, right? Or MacBooks or Apple laptops, right? They're more expensive because there are, compare the number of Apple laptops and non-Apple laptops, and you'll see the huge difference. Another example I told you in the previous session also, PlayStation, the latest PlayStation, which came, I think by intentionally, they made few number of PlayStations, so they get a lot of profit. And I remember it was very expensive. At least in my country, I heard in the news that it was very expensive in Iran, just because there were few number of PlayStations. So it became a fancy thing. When someone had PlayStation, the latest one, it was a fancy thing. It means that they were rich. Okay, so I think that explains everything. When one of them or both of them generate more, so you will have more products in the market, so you need to pay less for that, right? Right. So that's the thing. By the way, it's not just for products. As you see, we are learning life in this course too. So, for example, when you have some characteristic, when a person has some characteristic which is found rarely, this increases the value of that person, right? This is exactly this. This is the behavior that we see in this formula as well. Consider Einstein. Einstein has a brilliant brain, right? So Einstein becomes valuable because that quantity or whatever we call it, that characteristic in Einstein is very rare in the world. But what if we had the brain of Einstein across the world? Everyone was an Einstein. Then being an Einstein was not that much valuable because we have a lot of Einsteins, right? So that's the thing. Okay. So now the payoffs, pi 1 and pi 2. So consider pi 1 or payoff of the market 1. Sorry. So we have the profit, this is the profit, right? Times quantity 1, because that was the profit per quantity. So profit times quantity is the total profit for the for the player 1 or company 1. However, it's not, is payoff only restricted to profit? No, we also had marginal cost, right? We also had marginal cost. So minus C times Q1. And because C was the marginal cost per quantity for initial materials, etc., times Q1. And why times Q1? Because we're talking about company 1, right? So then multiply the terms to each other, simplify the terms. It becomes this, right? Pi 2 is the same, but we multiplied by Q2, the quantity of the company 2, right? Right? And when we simplify it, it becomes this. By the way, do you follow me? Because I don't get any feedback from you. Do you follow me? So what? Please interrupt me and be in the discussions. Challenge me. Otherwise, the course becomes boring. Okay, challenge me. So we have these two payoffs. And then what can we do? We can use the same thing that we learned for mixed strategies. So we can say first, we can use first order conditions, right? So in other words, I have pi 1 and pi 2. Let's take derivative. We want to maximize these payoffs, right? Let's take derivative with respect. So pi 1 is the payoff of the company 1, right? So, and its variable is Q1 because company 1 doesn't have any control on Q2, right? Company 2 doesn't have any control on Q1. Company 2 has control on Q2. As a result, I take derivative with this of pi 1 with respect to Q1. Why? So I have something, I want to maximize pi 1 with respect to Q1. It's an unconstrained optimization problem. What should I do? You remember? Guys, recall preliminaries. I have an unconstrained optimization problem. There is no constraint. I want to maximize some function with respect to something. What should we do? Yeah.
We did the first order derivative. Why is it unconstrained?
It's unconstrained. Where is the constraint for this? Inequality or equality. So we don't have any subject to what? We don't have. We don't have any restriction, right? So it's an unconstrained optimization problem. It's basically like, consider this is function pi 1. We want to maximize it. What do we do in high school? Take derivative, set it to 0, right? That was called first order optimality condition. So take derivative with respect to Q1. This part is linear with respect to Q1. It becomes this. This part is quadratic. It becomes minus 2Q1. This part is linear with respect to Q1. It becomes minus Q2. Set it to 0, right? And this derivative is also a scalar. Why? Because it's the derivative of a scalar with respect to a scalar. Yes. Yeah. Yes, I think we can take the second order derivative to check whether it's maximal or minimal or saddle point. But as you said, it's quadratic and it has minus behind it. What does it mean? It's concave. It's like this, right? So it has a maximum with respect to. Yeah, thank you. That was a good point. So we can also check the second order derivative. Then the second order derivative becomes minus 2, which is less than or equal to 0. So it's a maximum, right? It's not minimal or a saddle point. So when we set it to 0, this equation, let's call it R1. Okay. R1 is this equation is called in the competitions, I'm saying, in the finance, it's called best response function, also called reaction function. Okay. In management sciences, they call it reaction function or best response function. So the reaction function for player 2, again, we take derivative, set it to 0 with this, we take derivative of pi 2 with respect to Q2, right? And so this one, this is linear with respect to Q2, it becomes this. This is quadratic, it becomes minus 2Q2, and this is minus Q1. Set it to 0, it gives you this. Let's call it R2, which is the reaction function or best response function for our company 2. Right? We can also check the second order derivative, which is minus 2, correct. So it's a maximum, right? Now, so this is what we had. I'm repeating them. Okay. Now, what should we do? So for company 1 does this, right? To maximize its payoff. And we know that payoff has the profit minus the cost, right? So basic cost, they can't change it. As a result, they are thinking how to increase their profits, right? So R1 is for how to increase profit of company 1. R2 is for how to increase profit of company 2. What does Nash say? Recall Nash equilibrium in the previous sessions. What does Nash say? Nash says, yes. Yeah, exactly. So it's a situation where no one wants to deviate or no one has a profitable deviation. Yeah, thank you. That was correct. So now, as a result, what should we do? So this is an equation and this is an equation. For them not to deviate, both of these should be satisfied, right? As a result, you tell me this is equal to 0. This is also equal to 0. So let's equate these two equations to each other, right? As you see, Q1 equals Q2, and then let's put back Q1 equals Q2 in the equations. So basically, I have two linear equations, a system of two linear equations, and I'm solving it. Okay. I think you must have seen much harder system of linear equations. This is a toy, right? It's easy. So we find Q1 equals Q2, then put it back in one of the equations, such as which one? Such as the first one. So rather than minus Q2, I put minus Q1 because of this, right? Set it to 0. As a result, Q1 or Q2 equals this. So I'm solving this. It becomes 40 minus 3 over 3, C over 3. What was C in our example? It was 12. Do you remember in the previous slide? C was 12. So if I plug 12 in this equation, it gives us 36, right? So now what we did, let's show it geometrically in plots. So when I set these two equations equal to each other, basically it means that where do these two lines, because these are lines, right? They are linear with respect to Q1 and Q2. Where do these two lines intersect each other? So we know how to draw lines, right? From the equations. So we have R1. Sorry if this part is very easy. I try to teach it faster. So R1, set Q1 to 0 here. Then Q2 becomes 108 in this equation. Then set Q2 to 0. Q1 becomes 54. So this is a line, right? Why don't I go further in the line? Why am I only showing this part? Yes. Yeah, we know that you are saying that we know that they are intersecting here. No, there is another reason. Yes. Yeah, we can't have negative quantities. They are making chocolates, right? Can we make -1 chocolate? No. So we can have, these are generated quantities by the companies, right? So that's the reason. So now again, the other line in this equation, set Q1 to 0, it gives you a 54. Set Q2 to 0, it gives you 108. Where do they intersect? It's here. And where is it? Exactly what we found. Q1 is 36, and this is also 36, right? What we found here. This is called Cournot-Nash equilibrium. Cournot-Nash equilibrium. Okay? By the way, these plots, although seem very simple, but there are famous plots in finance. Okay? So Cournot competition is over. Now let's see the other competitions. These are famous competitions in finance. Stackelberg competition. But by the way, you see that quantities are continuous. I told you that quantities can be integer, but I think here, at least in these plots and these analyses, we are relaxing that. We are assuming that we might have float quantities too. For example, we might say the company generates 1.3 chocolates. Okay, so they are considering it as continuous. That's why it's a continuous strategy. As you see, Q1 is a continuous value. Q2 is a continuous value, right? Choosing Q1 and Q2 is the action in this case. So Stackelberg competition, it was proposed in 1934, much later than Cournot competition in reference 4. It has continuous strategy space, of course. It's a duopoly, so we have again competition of two companies in which two firms choose output levels, again quantities, in competition with each other, right? It is, well, how is it different from Cournot competition? It is sequential moves, right? So it's not a simultaneous move game. So order of game playing matters. Order matters. Because the second one will see the action of the first one, right? So every company makes, again, QI quantities, Q1 and Q2, right? Actions are choosing quantities Q1 and Q2 sequentially. So actions are continuous. How many chocolates? Marginal cost per making quantity, again, is C, like before, because they need to pay for the initial materials. Demand, or the total generated quantity, again, is Q1 plus Q2. We already talked about it, right? The profit per quantity, again, is as before. So again, the payoffs is similar to the payoffs of the Cournot competition. So pi 1 and pi 2. So it's profit times quantity, profit per quantity times quantity minus cost per quantity times quantity, as before. Now assume player 1 moves first without loss of generality, right? Without loss of generality, we can assume that player 1 moves first. What do I mean by without loss of generality? You see this terminology a lot in science, but yes, it means that doesn't matter. You can assume that the player 2 also moves first, and your analysis will be the other way around, right? So assume player 1 moves first, then the player 1 is named the Stackelberg leader, and player 2 is named Stackelberg follower. Okay, this is the terminology. So we have a Stackelberg leader and a Stackelberg follower. Now, okay, what happened? Assume player 1, as I said, so moves first. Player 1 predicts the reaction function of player 2 as was calculated in Cournot game. So basically, because what player 1 wants to choose, it should predict. I think the battery of this microphone is low. So player 1 should predict what player 2 will choose. So it chooses accordingly, rationally, right? So what did we have as a reaction function in Cournot competition, right? So we use that as the assumption for player 1. Player 1 assumes that the reaction function of player 2 is exactly its reaction function in Cournot competition, because everything is the same as Cournot competition except that it's a sequential move game, right? So R2 is this. Then as a result, so solve this equation for Q2. Of course, it will be a function of Q1. We don't have Q1 yet, right? So this, now we substitute this Q2 that we found in the payoff of Q1. Why? Because player 1 assumes that player 2 will choose the Cournot reaction function. Now, as a result, Q2 becomes a function of Q1. Then let's put it back in the payoff of player 1, right? So this was the payoff of player 1. Now let's replace Q2 with what we just found. It becomes this, right? I'm just simply plugging this Q2 here. Okay. Now what should I do? So now the whole thing here, the whole payoff 1 became a function of Q1. It's not a function of Q2 anymore, right? So I have payoff of company 1, which is a function of Q1. I want to maximize it. And I know that company 1 is in the control of, has the control over Q1. So let's take derivative, set it to 0, right? For maximization of pi 1, payoff 1. So of course, with respect to Q1, what is it? So this is linear with respect to Q1, it becomes this. This is quadratic, it becomes minus 2q1. Then this part is linear with respect to q1, becomes minus 60. This part is, this part is quadratic, becomes plus, so minus times minus becomes plus, and I have q1 squared over 2. Its derivative becomes 2q1 over 2. The two twos cancel each other. I will have q1. What about this? It's linear with respect to q1. It becomes plus c2, c over 2, right? Set it to 0 and solve it for q1. It becomes this. Now let's replace c with what we had. It was 12, right? In our example. It becomes 54, right? So we found that how many quantities that player 1 should choose, assuming that player 2 will be rational in the next reaction, right? Will be, because the player 2 hasn't played yet. So this is how we found it. By the way, we know that it's quadratic and it has minus behind it, so it's concave. As a result, we know that it's maximum, it's not a minimum or saddle point, right? So now what should we do? Recall this, which we had found from the reaction function of player 2. We just found q1. Let's plug q1 in this formula to find q2, because we know that player 2 is rational and will play according to the reaction function of Cournot game, right? Because everything is the same as Cournot game except that it's a sequential move game. So I put it back and I q1, rather I put 54, it gives me 27. And what is that? This is a Stackelberg Nash equilibrium, because it's good for both of them and they will not deviate. Yeah. Yes.
Why
No, so you're saying that why first off, why are they not equal to each other, these two? Because it's a sequential move game. Recall Cournot competition, it was a simultaneous move game, so they had to give equal amounts, generate equal amounts, right? But when player 1 generates first, so the amount of information that these two companies have differ. So why do you expect that they should generate the same thing?
Are they still getting the same profit?
The same profit? We should calculate. Let me think. We should plug back q1 and q2 in these equations. Let's do that. I haven't calculated. Pi 1. 120 minus 12 times q. What was q1? Sorry. 54. 54 minus 54 squared minus 54 times 27. Pi 2 is 120 minus 12 times 27 minus 27 squared minus 54 times 27. Okay, these two are equal to each other. Let's get rid of them. Do you have calculator? Let's calculate them. I don't know. And the reason that I don't know is that I'm not an expert in finance. Otherwise, I would know that. Excuse me. 108. So 108 times 54. 580. 2 minus 54 to the power of 2. 54 times 54. 2,916. So this is pi 1. Pi 2. 108. So we have this 108 times 27. 216 minus 27 to the power 27 times 27. Which one is less than the other one? It is. Although I calculated very fast, I hope I didn't make any mistake. Yes, I think it makes sense. Payoff of player one is large. If I didn't make any mistake. All right. Do you know why it makes sense? Player one moves first, yes.
Player two is making like the best choice they have available.
Yes, exactly.
It's still a worse payoff than player one, but it's better than anything else they could make.
Exactly. That let me tell this, repeat what you said to be recorded. So player one, of course, has advantage of first move, and player two, of course, his payoff is not better than player one, but it is doing the best it can. And it cannot get better than this. Why? If player two generates more quantity, the profit goes down. The total profit also goes down, right? So the player two can't make less than this because the profit also is multiplied by the quantity, right? Also, because of this, so there is a trade-off. Do you see the trade-off here? When you increase the quantity at some level is perfect, right? When less than that, this is an issue, this multiplier, right? Greater than that, this becomes an issue. Do you see that? Too much Q, the issue becomes in this profit per quantity, because when you increase Q1 and Q2, as I said, you will have a lot of Samsung phones. The profit goes down, right? However, if you generate much less than that, then you will not have enough profit, because the profit is multiplied. The profit per quantity is multiplied by the quantity itself too. So it's a trade-off. At some point, it's the best. Again, that sentence was great. So why is pi 1 better than pi 2 here? Because player 1 has the advantage of first move, and player 2 is doing the best it can as a response, right? So this is the plot of a Stackelberg competition. So we have R2. Do you remember? This was a reaction function for the player 2. By the way, why didn't we use reaction function of player 1 in this game? Can you tell me? We didn't use R1 in this game. In Cournot competition, we had R1. In this game, we never used R1. I think it's obvious by its name. What is the name of the function? Reaction function. What does player 1 react to? It is moving the first. It is making the first move. Player 2 should react to the other one, right? Okay. So R2 is this. Again, we can plot it by setting Q1 and Q2 to 0. You will get this line. And Q1 became 54. If you plot Q1 to this, it gives you 27 for Q2. So this point is a Stackelberg-Nash equilibrium. And as expected, this equilibrium is on the line, right? Because we know that the solution for player 2 must lie on the line, because it's reaction of player 2. Agreed? Yeah.
I might have missed it. Was there a reason that Q1 picked 54, or was that just a scenario?
No, it's a scenario because of C. C, I said it, let it be 12. Oh, yeah. This is an example. But the general plot is like this. The values might change, right? So the other competition, which is famous in finance, is Bertrand competition. So Bertrand competition, it was proposed in 1883. It is older than the Stackelberg competition. Okay. So it is again continuous strategy space. It's a duopoly. But in this case, the firms choose prices rather than the output levels or quantities. So you see the difference? They don't choose quantity this time. They choose the prices if in competition. Again, it has sequential moves. Sequential moves. And order of game playing matters, of course. Every company makes QI quantities, so Q1 quantities and Q2 quantities, right? And actions are choosing P1 and P2, not Q1 and Q2 this time. P1 and P2 from the range 0 to infinite, right? So P1 and P2 are the prices for the quantities in the market. Of course, we don't have negative price, right? What does negative price mean? Assume I have a chocolate bar and its price is minus $1. What does it mean? Whenever someone buys that chocolate bar, the shop should pay also that customer. That's a negative price, right? Of course, we don't have that in the real world. So prices must be greater than or equal to 0. 0 means it's free, right? So marginal cost per making quantity, again, is C for initial material. And the quantities are functions of prices. So this time, quantities are functions of prices. So like this, Q1, for example, is of course, we might have some constant. Again, these values might change. This is an example. 24, for example, minus 2 pi 1 plus 2 P1 plus P2. What does it mean? Let's analyze it. When you increase P1, what P1 means the price of Q1, right? Q1 is how many they generate, the product of company 1. P1 is the product, the price of product of company 1. When you increase the price P1, what happens? How many quantities can company 1 generate? Less, right? Because if every quantity is very expensive, when the quantity is very expensive for the customer, of course, it means that the quantity is also expensive to make in the company, right? As a result, the company can't generate too many of them. That's the reason of minus here. You see that? When you increase the price doesn't go up for nothing. The price for the customer goes up because the price for the company went up, the price of generating. As a result, the generation of company goes down, quantity goes down. What about P2? Why do we have plus here? Guys, I'm waiting for your answers. Why do we have? So what does this mean? When you increase P2, the price of company 2, the products of company 2, Q1 can increase. It makes sense. Why? Because it's a competition. When the product of the other company goes up, less people will buy it. Less people will buy it. So it gives more profits to the other company, and the other company can make more. Did you get it? Did you get it? Okay. So that's the reason of plus here. Likewise, we have for Q2. So the indices have changed, right? And as a result, the payoffs are these, pi 1 and pi 2. So pi 1 is quantity 1 times pi 1 minus C. What does it mean? Basically, it breaks down into two terms, Q1 P1 minus Q1 C. Similar to this we had in the previous competitions. So Q1, how many I generate times its price. Of course, what is this? Q1 times P1. What does it mean? How much money company 1 makes by selling Q1. So Q1 chocolate bars have been made by the company 1, each of which is sold to the customers by P1 dollars. So the whole thing which goes to the pocket of company, is Q1 times P1, right? What about these? However, everything is not profit in market. They also have costs to make. So Q1 times C, cost per making quantity in company 1, right? Agreed? So now I replace P1 with what we just, I replace Q1 with here what we discussed. We'll get this. Likewise, we have pi 2. The indices have changed, right? Agreed? So we calculated the payoffs. And what should we do? We want to maximize pi 1 with respect to Q1 because company 1 has control over Q1. So sorry. I just made a mistake and you didn't correct me. Here, the variable is not Q1 and Q2. Here, the variable is P1 and P2, right? In this competition, in Bertrand competition, the variable is not quantities in contrast to the Cournot and Stackelberg competitions. In this case, the variable is price, right? P1 and P2, we just discussed that. We just said it here. So we should take derivative with respect to P1 and P2. As a result, the company 1 has control over P1 and company 2 has control over P2. So take derivative with respect to P1. Take derivative of this with respect to P1, it becomes this. Set it to 0. It gives you this reaction function, right? So the way we found reaction function is different from the way we found reaction function in Cournot competition. Here, we take derivative with respect to P2, set it to 0. It gives us a reaction function for company 2. Okay. What should we do? For Nash equilibrium, they shouldn't deviate. So these two equations both should be satisfied, right? So they don't deviate. As a result, for them to be both equal to 0, it means that they are equal to each other. So I have a system of 2 linear equations. I'm solving them, right? And the variables are P1 and P2. So if you equate them, it gives you P1 equals P2. You put it back in one of them and you simplify and solve. So P1 and P2 becomes, so basically I'm putting this back in R1, I guess. It gives me this. P1 and P2 equals 8 plus 2C over 3. In this example, C is 12. As a result, this becomes 16. Then prices became equal. Yes. Just give me a second. I also have doubt about it. I guess, this is my guess. I guess I made a mistake here. I need to double check it and I'll let you know in the next session. I can't Google it right now. We can Google it right now. I don't know. Let's Google it. If I might have made a mistake. Bertrand competition. Wikipedia. Although people in science don't like Wikipedia, I think it's very informative. Is it sequential or is it simultaneous move game? Simultaneous is set a prime. I apologize. Sorry. Thank you. That was a great question. While I was explaining that, I also became in doubt. But your question made me think about it more seriously. So simultaneously, yes. Sorry about that. And an interest, so it's a simultaneous move game, and that's the reason we have both reaction functions. Otherwise, it didn't make sense to have reaction function for the first move, right? Sorry. So what should we do now? Again, thank you for the good question. Now I wanted to I just observed something. Sometimes when I'm teaching, I observe something myself. So I just observed something. So we talked about 3 games, although the 3rd game hasn't been finished yet. But let's take a look at the year of proposal. So Cournot competition was proposed in 1838. It was a simultaneous move game. The Stackelberg competition was proposed in 1934. It was a sequential move game. And Bertrand competition is a simultaneous move game, and it was proposed in 1883. What does it tell you? In ancient times, 18 something, they were thinking about simultaneous competitions. But later, in the previous century, they thought apparently we need some sequential move games too, competitions. Specifically, we are talking about finance. So what does it mean? At that ancient time, it wasn't that much important for them who moves first. They were thinking that people are choosing, competing at the same time. But nowadays, speed is very important. Speed is very important in marketing, right? Who moves first will have the benefit of moving first, right? In 1880, it wasn't that much important. This just told me, this observation just told me this, okay? And it was, I think, interesting. So we just found this. Of course, when it is simultaneous move game, if it is prices, the variables are prices, they must be equal because the amount of information between the companies is equal. If the variable is quantity, they should be equal, like in Cournot competition, because they have the same information. When it is a sequential move game, one of them moves first and will have better payoff, right? So they will be different. That's why they are equal to each other now. So here I have R1 and R2 reaction functions. Of course, they, as I said, according to Nash equilibrium, they should intersect, right? So R1, company 1 wants to be on this line, company 2 wants to be on this line. So where should they be not to deviate, not to wish to deviate, where they intersect? So again, we can calculate these lines. So set P1 to 0, it gives you in R1. P1 to 0, it gives you P2 equals minus 48. You might be wondering, it doesn't make sense. Minus $48, it means that the shop pays the customer $48. It says, please buy this chocolate bar from me. If you buy it, I will pay you money too. Okay. But why am I saying that? I'm just doing this for the sake of drawing the line, right? That's why I have put dots here. We don't go in these areas anymore, right? So this, and then you set, so P2 to 0 in R1, it gives you 12. Then you can connect these 2 points and it gives you this line, and only the positive part makes sense, right? Likewise, you draw R2, and where do they intersect? Here. And that's exactly the Bertrand-Nash equilibrium, right? And both in this example, they are both 16. So basically, it means that they both put it $16. So again, a scale is not important here. $16, 16 euros, 16 whatever pounds, $16,000, right? So scale is not important here. Okay, strategic substitutes and complements. So now let's compare. So we talked about the 3 competitions. Let's compare them. The Cournot and Bertrand competitions are having a strategic substitutes, okay, and a strategic complements respectively. So Cournot competition, its plot was this. Do you remember? Its plot was this, the left plot. This is in finance, finance and marketing. It's called strategic substitutes. These are terminologies used in those sciences. And Bertrand competition, its plot was like this. Do you see in the right hand side? It's called strategic complements. Okay. Do you see the difference of plots? Do you see that? And what does it mean? Let's see. Let's interpret them. In Cournot competition or strategic substitutes, if a company increases its quantity, the other company reduces its quantity. Let's take a look. So assume company 1 increases its quantity. What does it mean? I'm moving on the line R1 in this direction, because in this direction Q1 increases. Do you see this? And if I do that, what happens with the Q2? Q2 is reduced, decrease, right? Or in R2, if I want to increase Q2, so I should move in this direction. But in this direction, Q1 is reduced, right? So when one of them increases the quantity, the other one is reduced. However, in Bertrand competition or strategic complements, if a company increases its price, here the axes are price, the other company also increases its price. So consider PR1. By the way, in here, R1 and R2 are functions of price. Here, R1 and R2 are functions of quantities, right? So here, I want to, in R1, I want to increase P1. So I move here. Likewise, P2 increases. Or in R2, I want to increase P2. Likewise, P1 increases. So this was mathematical analysis. Let's come back to the real world. It makes sense. Consider two companies, Google and Meta. One of them increases its quantity. The other one, does the other one also increase its quantity? No. I think a better example is, again, Apple and Samsung. Samsung increases its quantity. Does Apple increase its quantity as well? No. Apple decreases its quantity. PlayStation and Xbox. Assume Xbox increases its quantity. Does PlayStation also generate a lot of PlayStations? No, it decreases the number of PlayStations. It's a rational move in finance. Now, take a look at prices. Again, Google and Meta. Someone increases the price. Assume, God forbid, assume ChatGPT completely becomes non-free, so that we have to pay for it. Assume the Bard, all right, Bard of Google also becomes expensive. So they both become. So ChatGPT is not free. Bard is not free also. OpenAI decides to increase the price of ChatGPT. Google will also increase the price of Bard. Right? This is how it goes. That's why inflation and these things happen, I think. Right? One of them increases, the other one also increases. Everyone increases their prices. Okay? You see that? These are rational moves. Okay. Acknowledgement. Some slides of this slide deck are inspired by teachings of Professor Stanko Dimitrov at the University of Waterloo Department of Management Science and Engineering. And some slides of this slide deck are based on this book, Eric Rasmussen, Games and Information, an Introduction to Game Theory. Okay, and these are their references. Any question? No? Okay, let's move on to the next topic. It's dynamic games. Dynamic games. Yes. So, dynamic games. When the game, what is dynamic game? When the game has some ranges and parameters, the game becomes dynamic. So some parameter does not have some specific value. It has a range of values, right? And we need to find those ranges. Hence, we call that game dynamic, because it's dynamic, right? Based on the range changes, right? In dynamic games, we can find the ranges of parameters which are suitable for the player's payoffs. You see that? Okay. Example 1. By the way, this example is example for courts. Do we have any student here from studying courts and law and these things? No. It's very interesting, and it talks about how. So we have game theory. I think the whole course are game theory. Okay. Someone who sues and someone who's against. So the defendant and plaintiff and defendant, they are playing a game, especially in US and Canada. And these so because they can resolve the issue behind the scenes. Do you know about these things, rules? So for example, someone says, I want to sue you. Either you give me some money, they decide how much money you should give me, or I will sue you in the court. So basically what law and law suing in US works in is this. Someone goes with the lawyer to another person that says, either because of this problem, pay me this amount of money, usually a large amount of money, $1 million, or I will see you in court. Okay. And I think you see this once in a while among celebrities, right? They do that a lot. Okay. So I think Trump had the issue that the other celebrity also, I don't remember their names. I'm very bad with names. Had those issues. Okay. What was the Jack Sparrow? Do you remember that? What was that? The actor of Jack Sparrow? Johnny Depp and his wife, his previous spouse, Amber Heard. Yeah, they had the issue, the same issue. They were suing each other, saying that you should pay me $1 million, $2 million, something like that. Okay, so the order of playing. So we have players, plaintiff and defendant. The order of playing game is this. So the plaintiff decides whether to bring the suit against the. By the way, plaintiff is the one who sues. Okay. The plaintiff decides whether to bring suit against the defendant who has been sued against, right? At cost C. So what does it mean? Of course, suing is not cheap. Otherwise, everyone would sue in US, right? So it is not cheap because you need to pay for lawyers, etc. The court itself. So it has some cost C. So plaintiff decides whether to bring suit against the defendant at cost C. Then the plaintiff makes a take it or leave it settlement offer of S greater than 0. So the plaintiff says to the defendant, whether you pay me S dollars or we'll see you in court, right? The settlement offer, right? Of course, they do it with lawyers. And the defendant accepts or rejects the settlement offer. Of course, if it is too large, the defendant might not accept it. If it is not that much large, then they might accept it. If the defendant rejects the offer, the plaintiff decides whether to give up. Basically, it means that whether the plaintiff was bluffing, right? Or go to trial at cost P, cost of lawyer to itself, and cost D to defendant. Of course, when the plaintiff brings the suit to the court, it will have costs for both the plaintiff and defendant, but the costs will be different. So the cost P for the plaintiff, the cost of lawyer, and the cost D to defendant, okay? If the case goes to trial, the plaintiff wins amount X with probability gamma. Of course, it's a probability thing, right? With probability, and you know that there's a lot of probability. Maybe that day the judge was happy or not. That also has effect. You might be wondering, no, but I think it has effect. Even when you apply for the study permit in Canada, I believe whether the officer is happy or not is also important at that day, the time of day. So if the case goes to trial, the plaintiff wins amount X with probability gamma and otherwise wins nothing. Okay, that's one thing. So the payoffs here in this, now I'm showing this, as you see, it's an ordered game, sequential move game, and I'm showing it with extensive form, and the payoffs are plaintiff and defendant. Okay, so P stands for plaintiff, the nodes P, then the nodes D, node D stands for defendant. So P either sues or does nothing. Okay, so if the plaintiff does nothing, the payoff will be 0 for both because nothing happened. Okay, if the plaintiff sues, then the plaintiff decides whether they offer settlement of S, meaning that, hey, defendant, do you want to pay me S dollars or not? If the defendant accepts the settlement, the defendant will pay S dollars to plaintiff. So its payoff becomes minus S because they have paid S dollars, right? But what happens to the payoff of the plaintiff? It becomes S minus C. Why? S dollars because they got S dollars from the defendant, minus C because of the cost of suing. This part had cost C. Okay, then the defendant might reject, say, no, you are bullying me, I don't pay you. Okay, so then the plaintiff decides whether to give up or go to trial. If the plaintiff was bluffing or is tired, they will give up. So the plaintiff loses C dollars because of the cost here, C dollars. And nothing happens to the plaintiff because to the defendant, because plaintiff was bluffing. So 0 payoff for defendant. But if the plaintiff goes to trial, then the payoff of the plaintiff becomes gamma X minus C minus P. Why? Gamma X, gamma is a probability. We saw similar thing in mixed strategies, right? Gamma, with probability gamma, plaintiff wins. So gamma times X, how much does it win? Do they win? Amount X. So gamma times X, and gamma is a probability between 0 and 1, right? Minus C because of the cost here, minus P because of the cost here. So do you remember I told you that this part has P dollars cost, P cost for plaintiff, D cost for defendant. Here I said it. Okay. As a result, in this part of the tree, the payoff of the defendant becomes minus gamma X because the plaintiff won gamma X. So the defendant will pay gamma X, right? Minus gamma X, minus D because of this cost. Yes. Expected value. Usually when yeah, it depends on. So it depends on whether you have several cases here. So when do we have expected value? When we have several situations, each of which has some probability, right? So I'm saying that gamma X, I think we can see it as expected value with only one value, possible value. What was expectation of X? Summation of X, probability of X over possible values of X, right? And probability of X is gamma. Gamma X means that we don't have several case scenarios here. In this part of the tree, we only have one either, right? Wins. So When do we have expectation? When we have several scenarios or several situations, each of which is probabilistic. In this tree, we only have this part which is probabilistic. The other parts are not probabilistic. They're deterministic. If you have probabilistic payoffs here, then you could say what is expected payoff over all scenarios. Okay. So any other question? So this is now let's see. The plaintiff sues if, you tell me. We are assuming that they're rational. Of course. So what are the payoffs of plaintiffs? 0 here, S minus C here, minus C here, gamma X minus C minus P here. Of course, these payoffs at the end of the tree, they should be larger than 0. Otherwise, is the plaintiff crazy to go to that part of the tree? Because if the plaintiff does nothing, they will get 0. So as a result, S minus C here should be greater than 0, or S must be greater than C, right? Also, this part should be greater than 0, or gamma X minus P should be greater than C. Agreed? Of course, minus C is not greater than 0, but we might end up here or here. So it still makes sense to come here if these two are satisfied. Okay. In case the plaintiff sues and the defendant rejects the settlements. So I'm saying that sues here, rejects the settlement. So this part of the tree. Okay. The plaintiff will go to trial. So this part of the tree. If, of course, this payoff is greater than minus C. Otherwise, the plaintiff will give up. Of course, the plaintiff will go through trial if this payoff is greater than this payoff. Otherwise, is the plaintiff crazy? Right? So gamma X minus C minus P must be greater than minus C. These two cancel each other. As a result, if gamma X is greater than P, then it's worthy for the plaintiff to go to trial. Right? Do you see? I'm finding ranges. This is called dynamic gain. Right? The plaintiff prefers the settlement. So the plaintiff prefers the settlement to not suing at all. So not suing at all, the plaintiff, its payoff is this. Settlement, if the defendant accepts that, its payoff is this. So S minus C must be greater than 0. As a result, S must be greater than C. Otherwise, the plaintiff even doesn't start the process. Right? The plaintiff prefers a settlement to trying again. So settlement, hopefully defendant accepts that, to trying again. This is a trying again, right? So this must be greater than this. As a result, S must be greater than gamma X minus P. So far, I'm talking about plaintiff. We can have similar discussion on the payoffs of the defendant. Yes. Which one? Two. Okay. Yes. Okay, I get your question. Let me think about it. So you are saying that equation 3 is implicitly satisfied by equation 2. This is what you're saying. Okay. So question 2 says whether we sue or not. Equation 3 says whether. No. So what I mean. So this is a matter of time. Here, the plaintiff is here. Wants to find out whether they should start the process or not. Here, the plaintiff is here at this node. Whether, am I right? go to trial or give up? What? In this case, I'm saying that if gamma x is less than p, so you basically, your question is, if gamma x is less than p, then in the initial point, the plaintiff wouldn't even start. Yeah. I think it's a good question. Yes.
I think it's not a strict condition to start shooting. Because if the S minus C is large enough, like you can also bet that.
Yes. So what you're saying, and why am I repeating this? For this to be recorded also. So you're saying that if this is S is much greater than C, even if this is not satisfied, the plaintiff might start. And if the plaintiff is in this node, then they will probably check this, equation 3. Yes, I think you're right. You can. So I think you can say that this is kind of an XOR thing. Again, it depends on the values of S and this thing. So if S is much greater than C, the plaintiff might say, what if the defendant accepts and I end up with here in the tree? If that's the case, then even if gamma x minus C minus P is not greater than 0, I might start again. Yes, that was a good analysis. Thank you. Any other comment? No? So, where did I stop? I already talked about all of the equations in this slide, right? So let me go to the next slide. Now we have bargaining. Bargaining is an important topic in game theory, okay? This part is related to bargaining. So the plaintiff, of course, we have bargaining here because of the settlement, right? Offer. So the plaintiff prefers settlement if this, I'm talking about plaintiff for now. Plaintiff, if this is greater than this, right? Because of course, the defendant should decide whether to accept it or reject it, but still we can talk about the preference of the plaintiff for the settlement. What happens, what should satisfy if the plaintiff wants to go in this direction rather than going in this direction? Of course, when S minus C is greater than gamma x minus C minus P, right? If this happens. The defendant now, let's talk about defendant. The defendant prefers settlement, so this part of the tree. If minus S, now I'm talking about defendant, so I should consider the payoff of the defendant. If minus S is greater than minus gamma x minus D, right? So preferring this part over this part by the defendant. So S must be less than gamma x plus D. What does it tell you? Take a look at this. This became interesting. The plaintiff wants I want to find the amount of S. The plaintiff wants S to be greater than gamma x minus P, right? The defendant wants S to be less than gamma x plus D. Of course, it makes sense because plaintiff wants larger S, right? The larger S is better for plaintiff. Give me $10 or give me $1,000, which is better for me? $1,000, right? So the plaintiff wants larger S. The defendant is the other way around, wants smaller S because they need to pay. But what range do they want? So these are the ranges. We just calculated them. What does Nash tell you? Nash equilibrium. Hey, Nash, rest in peace. What does Nash say? Nash says we should find somewhere where everyone is happy and doesn't want to deviate. Of course, both should be satisfied. Both equations 6 and 7. When does this happen? When S is equal to gamma x plus T. By the way, you can see this as greater than or equal to, right? Or less than or equal to. So for these two to happen, what it is when S equals gamma X plus T. So we just found out how to find S. This is exactly the bargaining thing, right? At least in my country, we see this a lot. I haven't seen that much in Canada. When you go to a shop, the seller says, this is this amount of dollars. The customer doesn't accept it. Say, for example, $1,000, the customer said, no, I'll give you $500, right? The seller says, no, it's too low. But the seller comes down a bit, says maybe 750. So they are changing their expectations. They are changing their prices until they agree on some part. This is exactly what happens. So the plaintiff goes to the, you tell me, the defendant and says, give me gamma X plus D plus $1, plus $10, right? Then the defendant says, no, I will give you gamma X plus D minus $10. Then they change their values until they agree on gamma X plus D dollars, right? This is Nash equilibrium. Before that, they wanted to deviate. When they reach gamma X plus D, both are happy. That was example 1. Example 2 is the same, but with some changes. Again, we are in a court, okay? Difference is that the plaintiff pays in advance without any refund if the case settles. I think many lawyers want that, right? So the plaintiff must pay in advance without any refund if the case settles. So as a result, I have minus P here, also minus P here. Previously, I only had minus P here, but now these two have been added. The price, right? This is more realistic case because usually lawyers will not give you back money. When you pay a lawyer, it's gone, right? The plaintiff sues if, what happens again? Sues. So of course, if this and these, no, this is negative, but these and these two are greater than 0 here. So these, as a result, S must be greater than C plus P, and gamma X minus P must be greater than C, right? In case the plaintiff sues and the defendant rejects the settlement, then what happens? So the plaintiff sues, we are here. The defendant rejects, we are here in the tree. The plaintiff will go to trial here if, we are talking about plaintiff, if this is greater than this, of course. When gamma X minus C minus P is greater than minus C minus P. Of course, when gamma X is greater than 0. What does it mean? I think it always happens. Gamma is a positive probability, and X is something that they will gain. Unless X is 0, then this doesn't happen, right? When the plaintiff prefers the settlement, the plaintiff hopes that this happens if S minus C minus P is greater than 0. Otherwise, they will not even start. So if S is greater than C plus P. The plaintiff prefers a settlement to trying again. So settlement this to trying again this one. Of course, when S minus C minus P is greater than gamma X minus C minus P. We are talking about plaintiff. So when S is greater than gamma X, right? I think it makes sense. Gamma X is the amount that they will gain. S is the amount that they will gain if the settlement is agreed on, right? Right. Again, bargaining in this case. The plaintiff prefers settlement if, so plaintiff prefers settlement if this is greater than this. We already talked about it. If S is greater than gamma X, right? Now, what about defendant? So I want to find the settlement offer S, the amount of how many dollars should they settle on, right? The defendant now prefers settlement this part over this part if minus S, because we're talking about defendant, is greater than this part, right? Minus gamma x minus d. So if you rearrange, S must be less than gamma x plus d. Now do you see this has changed? Equation 13 changed compared to the previous example. So plaintiff wants larger S. They say S must be greater than gamma x. The defendant says S wants a smaller S, says S must be less than gamma x plus d. Then what happens? As a result, S must be intersection of these two ranges. S must be between gamma x and gamma x plus d, right? So this is settlement range. But so we didn't find only one value. We found a range for S. What can you tell me? Does any value here do they settle on any value here? Of course. Who offers the settlement? Can you tell me? Who offers the settlement? The plaintiff or the defendant? The defendant offers this. No. Who says that how much money? The amount of money of settlement. The plaintiff, right? The plaintiff goes to the settlement and says, to defendant. Hey, defendant, pay me this amount of money, otherwise I'll see you in court, right? So the plaintiff says that. The plaintiff wants larger S, right? And the plaintiff also knows that, again, common knowledge, that the defendant is also rational. So according to common knowledge, they both know that S must be in this range. What value in this range will the plaintiff offer? Of course, the greater value, right? Because wants more money. So S will be gamma x plus d offered by the plaintiff, right? Agreed? Did you understand? Any question? No? Yes.
So is it the same for example 1? Is that settling range for example 1 of it?
So example 1 is that is settled amount was gamma x plus d, but they had to. There was no range for it. The intersection of these two was only this, right? The plaintiff didn't have any choice but to choose this. Otherwise, the rational defendant would reject. In example 2, there is a choice of range for the plaintiff to offer, but the rational plaintiff wants more, right? So they will choose gamma x plus d. And they know that if they choose gamma x plus d, the defendant will probably agree because it's a Nash equilibrium. Okay, you see? And here is a range because it's a dynamic game. Any other question? No? So acknowledgement. Some slides of this slide deck again are inspired by teachings of Professor Stanko Dimitrov at the University of Waterloo Department of Management Science, and this book, Eric Rasmussen, Games and Information and Introduction to Game Theory. And this is the reference, okay? Before we have a break, let me finish game theory, and I think one topic is left in game theory. Repeated games, not long. It's not long. Okay. Repeated games. So in the repeated games, are you tired? You want to have a break? I don't know. Do you want me to finish this and then we'll have a break, or do you want to have a break right now? Finish this? Finish. Which one? Raise of hands, break. Raise of hands, not have break after this. Okay, let's have a break and come. Okay, let's resume. So let's talk about repeated games. This is the last slide taking game theory in this course. So in the repeated games, players make actions repeatedly in the same setting. So the same setting repeats over and over, right? So repeated games are different from one-shot unrepeated games. So far, we usually talked about unrepeated games. They are one-shot, right? Now, repeated games occur repeatedly. So finitely repeated games. In the finitely repeated games, players make actions repeatedly in the same setting in the finite number of repetitions. So the number of repetitions is finite. What does it mean? The game will end. After some repetitions, the game will end, right? So in finitely repeated games, after some finite number of repetitions, the game ends. There are two ways to find the equilibrium strategy in finitely repeated games. How? Either solve it because it's repeated, right? The same setting is repeated for finite number of iterations. Then one way is to solve it from beginning, conditioning on previous history. Okay, so you start from iteration 1, then you go to iteration 2, conditioned on iteration 1, repetition 1, I mean. Then you go to iteration 3, conditioned on repetition 1 and 2, right? Or you solve it backwards, because you know it eventually ends, right? When it ends, solve it backwards. Solve it backwards from the end of repetition, because there is an end, because it's a finitely repeated game. Do you know Soren Kierkegaard? Anyone here? Kierkegaard? No? He's a very famous philosopher. He says one of the one of the continental philosophers, okay, because we have two types of philosophies: continental philosophy and analytical philosophy. So such examples of continental philosophies: Immanuel Kant, René Descartes, Spinoza. Spinoza is very great. I don't know if you have read his philosophy or not. Spinoza, Kierkegaard, Schopenhauer. Let me tell you more. Schopenhauer, I don't know, I forgot. Oh, Nietzsche, a very great philosopher. Nietzsche, etc. Right? So one of them was Kierkegaard. By the way, examples of analytic philosophers: Bertrand Russell, Gottlob Frege, Wittgenstein, Quine. Recent philosophers, all of them are almost in Canada, US, England. Most of the philosophers are analytical philosophers nowadays. In Germany and Greece, most of the philosophers are continental philosophers nowadays. Okay, so Kierkegaard says life can only be understood backwards, but it must be lived forwards. What a nice sentence. Life can only be understood backwards. So what does it mean? When you get old, when you are on the deathbed, you will understand whether you lived well or not. Right? What the decision that you made 30 years ago, was it a good decision or not? Right? But you have to live forwards, because we are causal. We don't know what happens in the future. Right? It's very great philosophy, I believe. Okay. So this is Kierkegaard, the figure of Kierkegaard. By the way, Kierkegaard also talks about faith. So faith is one of the important concepts in not religious faith, some kind of higher level faith in Kierkegaard's philosophy appears a lot. Okay, anyway, recall the prisoner's dilemma game. So prisoner 1, prisoner 2, consider this, do you remember? Consider the finitely repeated prisoner's dilemma game. Okay. At every time slot, the two prisoners choose their actions simultaneously, right? So what do I mean? So far, we saw prisoner's dilemma game in one shot. Now let's repeat it, right? And it in each repetition or in each iteration, both of them choose actions simultaneously, right? Right. So what, and it is finitely repeated. The Nash equilibrium of the one-shot prisoner's dilemma game is defect. Do you remember? Let's calculate it if you don't remember. So it's one shot. So if I'm here, prisoner 2, so 0 is better than -1, so here it deviates. If I'm here, -2 is better than -3, come here. If it is here, 0 is better than -1, better. If you are here, -2 is better than -3. Recall the lecture of Nash equilibrium. We talked about it. So as you see, this is the strong Nash equilibrium, a strict Nash equilibrium, defect. They will both defect, right? It's a one shot. So they will both suddenly defect. But now it is repetitive, right? Now let's do backward analysis. Because forward analysis that I said, forward analysis is very hard. This is very hard. Backward analysis is easy, according to Kierkegaard, right? So let's do that. Of course, in the last iteration, rational players should both defect, right? Because eventually, what is important, what happens eventually? Eventually, they both should choose defect action. Or there's an or too. In the 1 to last time slot, one or both of them choose defect. And if the other one hasn't chosen defect yet, in the last iteration, the other one will also choose defect. Did you get it? Either they will both wait, maybe cooperate. Suddenly at the end, they both defect. Or in 1 to the last iteration, one of them defects sooner and the other one feels the risk. And in the next iteration, which is the last iteration, the other one will also defect. Did you get it? Okay, so that's fine. This is the backward analysis. Yes. No, assume the prisoner's dilemma is happening again and again, and they can change their actions. But at every iteration, they are having the same, they are choosing the actions simultaneously at the same time. Did you get it? This is repeated games. So we talked about finitely repeated games, and I told you an example of backward analysis. Infinitely repeated games. In the infinitely repeated games, what does it mean? It's infinite number of repetitions. Infinite number of repetitions, so it's forever. They make actions repeatedly in the same setting. Again, the same setting. Simultaneously, they move actions. They make their actions, but it never ends. It's infinite number of repetitions. It's forever. There are, by the way, we'll see that it's either forever or the probability of ending game is very low. It's equivalent to being infinite number of iterations, right? When the probability of ending game is very low. An example of this is the world. There is a tiny probability that the whole world suddenly finishes. But why do you have hope for tomorrow? Because you are assuming that this world is infinite game, right? Infinite repeated game. We will have tomorrow, and we'll have the day after tomorrow. It will never end, because that probability of vault ending is very low, very, very tiny. Okay. So there are two ways to find the equilibrium strategy in infinitely repeated games. One of them is Grimm strategy. The other one is tit for tat, also called alternating approach. Okay, let's see. We want to explain these using an example of prisoner's dilemma game in the next slide. Okay, Grimm strategy and tit for tat. These are for infinitely repeated games. Recall this prisoner's dilemma game. Okay, consider the infinitely repeated prisoner's dilemma game. At every time slot, the two prisoners choose their actions simultaneously, of course. So Grimm strategy, it's this. It says start with cooperate action. They both start with cooperate action from here, right? And they continue to choose the cooperate action. Why do they start, by the way? Can you tell me, why do they start with cooperate action? Because it has higher payoff than these, right? Higher payoff. But why do we know that this is unstable, although it has higher payoff? According to Nash. Nash says, although that this cell, in this cell, they both have higher payoffs, but this is unstable. They will eventually deviate because of Nash equilibrium, because this cell is Nash equilibrium. I just showed you, right? So although in this cell, they have higher payoff, but they deviate. And the reason is greed. The reason is greed. We always have greed in game theory. Although it's better for both of them to stay in cooperate, but one of them will deviate to become better. And as the other, that one of them deviates, the other one must deviate. Did you get it? Okay. So start with cooperate action, then continue to choose the cooperate action unless another player chooses the defect action because of greed. Then choose the defect action. Did you get it? Why am I not worried that the other one might choose a defect? Because I still have time. If the other one chooses defect, I still have the next iteration to choose defect. But this not having worry doesn't exist in finitely repeated games. Why? Because in finitely repeated games, I will not continue to choose cooperate even at the last iteration, because I know that eventually the other one will deviate, right? Compare this strategy with the strategy in finitely repeated prisoner's dilemma. In finitely prisoner's dilemma, repeated prisoner's dilemma, they have the stress. We are two players. We both have a stress in our mind. What if the other person suddenly chooses defect? I should also choose defect. Otherwise, I will lose a lot, right? So we will wait. In the last iteration, we know that probably the other person is greedy. So let me choose defect. The other person will think the same, will choose defect. Did you get it? According to Nash equilibrium. But in infinitely repeated game, they don't have stress. Whenever the other person becomes greedy and chooses defect, I still have time in the next iteration to choose defect. Okay. Yes.
When finally repeated, you can ignore other options. Is that what you're saying?
So I'm saying that in finally repeated games, we know that the game ends. And in the last iteration, at least in the last iteration, I have the stress that there will, if I choose continue in the last iteration, cooperate in the last iteration, and the other person chooses defect, I will lose a lot. As a result, I will choose defect. The other person will also think the same. The other person will choose defect. That's the reason that in the finitely repeated game, in prisoner's dilemma, they will both choose Nash equilibrium in the last iteration. Yes. So no, so repeated games is this definition. In the repeated games, the game is repeated. Okay, and we see that a lot in the world. Who says that all of the games are in one shot? Sometimes we are repeating a game. The whole life is repeated game. You wake up, You eat breakfast, you go to work, you come back, you may take a shower, you eat dinner, you go to bed, you sleep, you wake up, it's a repeated game. Right? You see that a lot in the book. Okay. So another approach is this. Sorry, what? I didn't. Can you explain more? I didn't understand what you're saying.
Like, even if the game keeps going,
Okay.
players don't change their mind. It's like that's like the best choice for like.
So I'm saying that we know that this is better for them to stay in, but we know that according to Nash, they will deviate. If you are here, player 2 will deviate here according to Nash, because this 0 is better than -1. According to greed, right? When we say deviate, it means greed, right? Greed. If you change the payoffs, it will not be prisoner's dilemma anymore. It will be another game. And in that game, it might be a different game. But in this game, I'm saying that they will start with corporate and corporate because of higher payoff, but they will not remain there forever. Okay? Because of greed, because of deviation. Here, if you are here, also player 1 wants to deviate here because 0 is better than -1. When, for example, player 1 suddenly comes here, player 2 gets -3. It becomes risky for player 2. Suddenly, player 2 also deviates. Did you get it? Okay, this was Grimm's strategy. Tit for tat says both start with cooperate action again, but they will alternate. It's like they play a game, they alternate. So they do it periodically. Like, what is that game in? I don't know the name in English. We sit on something, we go up and down. What? Seesaw. That's exactly like seesaw. And the period is the amount that I go up and then I go down, right? So seesaw. Yeah. So in period N, choose the action that the other player chose in period N-1, right? So one of them chooses cooperate. In period N, so assume we both choose cooperate, one of them chooses defect. The other player doesn't choose defect suddenly. Waits for period N and will choose defect, right? So this is how it's going. And it is an alternating approach, as you see. So defect, cooperate, defect, defect, cooperate. And why do they have peace of mind to wait for period N? Because they know that the game will not end, right? Because it's an infinite game. And in this case, expectation happens. Expected payoff, right? So we know that expected payoff, its average payoff or expected payoff is less than a strategy cooperate or cooperate. This is an example showing that how greed can be bad for the whole world, right? If they were not greedy, any of them, in other words, if they didn't want to deviate because of higher payoff, they would both stay here and they would both benefit more. But because of greed of one of them, the other person also needs to become greedy, right? You see, okay. So there is an important theorem in game theory named Folk theorem. I don't prove it, we talk about it. So Folk theorem, it's about repeated games. The formal statement of Folk theorem is this, references 1 and 2. In an infinitely repeated n-person game, so it's infinitely repeated, n-person game, we have n players, with finite action sets, so we don't have too many possible actions, right? At each repetition, any profile of actions observed in any finite number of repetitions is the unique outcome of some sub-game perfect equilibrium given. By the way, this is a formal definition. I know it's a bit hard to understand, but we'll see easier explanation of Folk theorem too, okay? So conditions are important. Condition 1, condition 2, condition 3, and I will tell you what this theorem is saying. Condition 1, the rate of time preference is 0 or positive and sufficiently small. I'll tell you what it means. Condition 2, the probability that the game ends at any repetition is 0 or very small, positive and small. I already talked about it. Condition 3, the set of payoff profiles that strictly Pareto dominates the minimax payoff profiles in the mixed extension of the one-shot game is n-dimensional. Okay. This was a formal definition, but let's go to see what it means actually. First off, what it is saying is this, that if an infinite time remains in a game, okay, then there is always at least one player that will punish another player. Greed, right? Greed. That will punish another player in order to guarantee a better future. Okay? Even if the punishment hurts both parties. That's weird. We see that in life a lot. It's a combination of greed and jealousy. Jealousy, right? In jealousy, you might destroy another person even if it hurts you. Right? Haven't you seen such cases? That the person says, I will destroy you even if I go down myself too, right? So this, and it has a mathematical proof. Did you know that the behaviors of humans in the world has mathematical guarantee, mathematical proof, okay? Why do we have jealousy in this world according to math? Okay, so because the world, the life is assumed to be infinite time, right? Again, it's assuming that it is infinite time. Why when someone is close to death, they will not have jealousy much because they know it's a finite game. But when you are young, we assume that it's an infinite life. Then the folk theorem applies to us. And the folk theorem says that the young people might become jealous more, right? Because when someone is old, they'll say, I don't have much time. Why do I hurt both of us? Right? This is the reason. Any finite time period is insignificant relative to eternity. Okay, that's another thing that folk theorem is saying. So let's talk about the three conditions one by one. Condition 1, discounting. With discounting, the present, by the way, this discounting is also appears in reinforcement learning. We'll see that. Okay. So with discounting, the present gain from defecting is weighted more heavily than future gains from defecting. So assume we have defecting. Assume if I defect sooner, I will gain more than in 10 iterations, right? So when we have defect, the greed becomes higher. Because I will get greedy sooner. Because when there is no discount, when there's no discount, I will say, doesn't matter if I defect in 10 years or now, right? When I defect, the other person will also defect. But when there is discounting, I know that if I defect tomorrow, it will be less benefit for me than defecting now. So let me defect now. Okay. So if now assume the discount rate is high, very high. What happens? Very, very high. The infinitely repeated game reduces to a one-shot game. Because in the first iteration, first ever iteration, they will both choose defect. That's exactly the one-shot prisoner's dilemma, Nash equilibrium, right? So the game almost becomes one-shot. If the discount rate is 0 or very low, then it becomes an infinitely repeated game, right? Agree? So by choosing discount rate, you can have an interpolation between one-shot game and infinitely repeated game. A middle case scenario, all right? Condition 2, probability of game ending. Let the probability of ending the game in the repetitions be denoted by theta, which is greater than or equal to 0, according to the properties of probability, right? If theta is large, what does it mean? The game ends with high probability in every iteration. So the game will become finitely repeated game, right? If theta is very high, I can say it becomes again one shot, right? Right? But if it is maybe half, even half is large, not very large, not very close to one, but if it is half, even half, then it's not an infinitely repeated game. It's a finitely repeated game. If theta is very large, as I said, very close to one, it becomes one shot game. If it is very low or 0, the game becomes infinitely repeated game. Again, I told you an example of very low. This world. There is a tiny, tiny probability that this world ends tomorrow. But we still have hope for tomorrow for 10 years, right? Because we assume that it is an infinitely repeated game. Condition 3, minimax. You have a question in assignment about it, yes? These are the conditions in folk theory. Yeah, so they are talking about the folk theorem, the whole thing is talking about infinitely repeated game. So if you have these 3 conditions, then it is an infinitely repeated game. It's talking about infinitely repeated game. So basically, it's discussing, I can say. It's discussing, for example, it's discussing about discounting. If discounting is high, then it's not an infinitely repeated game, right? Because it's a one-shot game. Agree? So if by the way, what I'm saying linguistically, folk theorem proves it mathematically. Okay, I'm talking about it in English, not in math. So probability of game ending, if probability of game ending is large, very large, and it becomes one shot. It's not an infinitely repeated game. If it is not very large, but it is still high, it becomes a finitely repeated game. It's not an infinitely repeated, right? Any other question? No. Minimax. So minimax strategy. You see, I think this is very important. The minimax, you see it a lot in machine learning in different areas of science. So the strategy in which all the other players pick a strategy solely to punish player I. Assume you have several players. All of the players except player I will want to punish player I. What is it in real world? What is it called in real world? Gang up on player I, right? All of the players gang up on player I, right? The player I, of course, gets protects itself from this gang up, right? Everything in game theory is real world life. So then the set of strategies S minus I star is a set of n minus 1 minimax strategies chosen by all players except player I. So this is my notation. S minus, do you remember we talked about it at the first lecture of game theory? S minus I is the strategies of all of the players except player I. S minus I star means the optimal strategy, right? For the other players. To keep the payoff of the player I as low as possible. What is the optimal strategy of the other players? What is the optimal strategy of other players here? To have the lowest payoff for the player I, ganging up, right? Gang up on player I. So they want to punish player I, no matter how it responds. They don't care how the player I responds. In other words, S minus I solves what? Do you see that? Yes. What? Yeah, it's exactly optimization, But consider these two. One of these sentences says the other players gang up on one player. The other sentence says the player I protects itself. Is it one optimization problem or two optimization problems? Two. One for gang up, one for protection. Right? So that's why we have mean max. This equation 1 is two optimization problems written in one line. Okay? So minimize pi I with respect to s minus I. What does it mean? So this minimization is done by all other players except player I. This maximization with respect to SI is done by player I. Right? Pi I is the payoff of the player I. As you see, interestingly, other players, they don't want to increase their own payoffs. They want to punish player I. They want to minimize the payoff of the player I. Gang up. All right? But the other player wants to protect itself. So, of course, this pi I is a function of Si and S minus I. The payoff of the player I obtained from the above equation is called the minimax payoff, or minimax value, or security value, because that person wants to secure themselves from the gang up. Right? By the way, yeah, we'll talk about it. Okay. Now, maximin strategy. Maximin. So the previous one was minimax. Minimax, minmax. Maximin, maximin. Right? The strategy in which an offender trying to protect itself from the punishment. So let's talk about minimax and maximin, compare them. In minimax, player I maximizes its payoff, and the others minimize that maximum payoff of player I. In maximin, the other players minimize that payoff of player I, and then the player I maximizes its payoff, which was minimized by the others. Do you see the order? Let me come back to this equation 1, minimax. What is the order of optimization? When you say minimize, maximize something, what is the order? Minimize, maximize something. What is the order? Any answer? What? That's fine. If it is wrong, that's fine. You're saying that the order is minimize then maximize. But what if I write a parenthesis like this? Of course, this parenthesis is implicit, because this is an argument of maximize first. Then the whole thing is an argument of minimize. Right? So when you say min max, the order is first max, maximize, then minimize. When you say maximin, the order is the other way around. This is maximin. Maximin. You first minimize with respect to S minus I, and then you maximize with respect to SI. Did you understand it mathematically? Right. Now let's understand it intuitively. What is the difference of this in terms of bullying and ganging up? Equation 1 versus equation 2. Equation 1 says other players come to player I and say, we want to gang up on you. The player I says, let me maximize my payoff so they don't gang up on me, right? So the player I first maximizes payoff because felt the risk, the danger, right? Then the other players minimize that maximized payoff. Punish that maximized payoff by player I, okay? Equation 2 is the other way around. The other players come to player I, they gang up on them, on that person. Then after that person is damaged, then they will try to maximize their payoff. Did you get it? Did you get it? Okay. So the strategy SI star, in this case, I have SI star, is a is a maximin strategy for player I if given the other players pick strategies to make the payoff of player I as low as possible. SI star gives the player I the highest payoff, possible payoff. In other words, this is the maximum. Okay, I already explained this. In maximin strategy, every player protects itself from the worst harm possible. Do you see the difference? In minimax, they will increase their payoff. Player I increases its payoff. The other ones punish, to hurt the maximized payoff. In equation 2, maximin, the player I waits for them to do the worst punishment that they can do, and then they will increase that, right? So in other words, in equation 2, in maximin, the player I considers the worst case scenario. Worst case scenario for player I, right? Because of this is worst case scenario. Minimum. The maximin and minimax strategies have opposite order of optimization, as I explained, right? So in our assignment, also order of optimization, be careful about that. The minimax theorem, we have a minimax theorem that's important. Minimax theorem. Reference to minimax equilibrium exists in pure or mixed strategies for every 2% zero-sum game, and it is identical to maximin equilibrium. So there was a very interesting question that you didn't ask me. Are the solutions of minimax and maximin equivalent? Under some conditions, yes. And what are the conditions? First, it needs to be a 2% game, right? Then it needs to be zero-sum game. Whatever one of them loses, the other one gets, right? And the summation of payoffs becomes 0. We talked about zero-sum games before, right? In this case, if you change the order of optimization, the solution will be the same. Can you tell me an example of this in machine learning? In machine learning, we have minimax or maximin, which is actually a 2% game, and it is a zero-sum game. And this minimax theorem explains that why it doesn't matter in what order we start the optimization of that machine learning algorithm, because min-max will be equivalent to max-min. By the way, you understand that when I say equivalent, I say, for example, min, max, pi, something, for example, x, y, then I mean max with respect to y and min with respect to x. Of course, when it is min with respect to x, here needs to be min with respect to x. I didn't mean min with respect to y, okay? These two will be equivalent under these conditions, okay? An example is GAN in machine learning. Let me tell you about GAN. So an example of minimax game strategy in machine learning is generative adversarial learning, or generative adversarial network, GAN. Proposed in 2014 by Jan Goodfellow et al., Yashua Benjo et al. Okay. They were in Université de Montréal. Okay. So let me tell you about this. It's very interesting. Forget this slide for now. Consider this a story. I want to generate some images which seem realistic. Okay. For an example, I want to generate some facial images which never existed in the world. Don't exist, right? And then, of course, I need to judge it, right? For example, I need to judge whether this generated image is good enough or not, right? Of course, agree? Then something comes which is very crap. I say, oh, it's very bad. Something comes that I become doubtful whether it's real or whether it's fake, right? So the best way to do this judgment is human visual system. Human visual system. Because we are designing this for humans. If we were designing that for dogs, the best judge was dog, right? But you are designing this system for human. So humans visual system is the best judge. But can we take, in machine learning, everything is optimization plus some other things, such as linear algebra, probability. So everything breaks down into optimization in machine learning. So I need to define a cost and take derivative, right? Because in optimization, you have to take derivative. Can I take derivative of humans' judgment? Can I take you judge something? Can I take derivative of that? No, right? So we need to replace humans' judgment with something. What do we put as a judge for whether some generated image is good enough or not? Can you give example? Classifier. So I can put a classifier to decide whether to binary classes, whether it's real or fake, right? Of course, I need to train the classifier. So someone might say, let's train a classifier completely, and then we use this pre-trained classifier for judgment, right? And I have something else which generates images, and I feed it to the classifier, say to decide whether it's real or fake. Right? So I have two things. One of them is generating, the other one is judging. As you see, we have two players, two agents, two players. It became a two-player game, right? One generator, one classifier. Or they also call it discriminator, classifier or discriminator. Discriminating fake from real, right? However, we can improve it further. One might say, we are in the mind of, by the way, whenever you want to understand an algorithm, put yourself in the shoes of the designer of algorithm. You should assume it's the year 2013, 14, around that time, and you are in the mind of Goodfellow, right? What was he thinking when he was developing this algorithm? Exactly this that I'm telling you. So he says, let's have a classifier or discriminator. But maybe he has a meeting with Yoshua Bengio, his supervisor, comes back and thinks a bit, says, why do I need to have a pre-trained classifier? Because I need to train that generator, right? Let's train the classifier at the same time that I'm training the generator. Let's train them simultaneously. Suddenly, he remembers the game theory course that he had passed. He says, isn't it a simultaneous move game? Or at least a two-player game? One of them is generating, one of them is checking whether it's real or fake. Apparently, these are enemies. The better the generator becomes, the more realistic images become, the more we fool the discriminator, right? The better the discriminator becomes, the harder it becomes for the generator to fool the discriminator. So they are enemies. Apparently, it's a zero-sum game. Whatever this gains, the other one loses, right? So that was the time that Goodfellow found out whatever he's thinking of is a game theory. Is a game. Okay. Then he said, okay, let me train them together. So let's train them simultaneously together. So this was the concept. Now, this is the figure that he drew in his notebook before going to Yoshua Bengio's meeting. Right? He says, I have a data set. So, of course, whenever I want to make realistic facial images, I need to have some actual facial images too to train from, right? So I have a data set of actual facial images, real facial images. I get X from that. So X is this means sampling, sampled from data, probability of data. So this distribution of data, right? Basically it means I get it from the data set. So this is X, real X. I also make a generator generative models or generators in machine learning, they usually get random noise and output something corresponding to that random noise. Okay. We have different generative models. One of them is variational models. One of them is adversarial models. Okay, we have different ways to do that. This is adversarial way. So what do I mean? Anyway, most of the generative models take some noise, such as Gaussian noise, right? Some noise. And it says that this noise corresponds to some realistic thing, right? You get it? For example, we are real, right? I am corresponding to Gaussian, for example, with mean 0.1. It's consider this Gaussian distribution. This point corresponds to Benjamin, for example. This point corresponds to you, for example, right? When you move on this part in the Gaussian distribution, each of these points corresponds to one of us in this class, for example. Assume so this is a generative model. As a result, Z, also called latent variable, because it's hidden, latent variable or noise, latent noise, whatever, is derived, is sampled from some Gaussian distribution, for example, right? And I feed it to G, and it gives me X. G stands for generator, generative one. D stands for discriminator or classifier, right? So it gives me X, which has some probability. Why do this is a smaller and this is larger? Because usually the dimensionality of noise is small, but the dimensionality of X is large, the number of pixels, right? But the discriminator is the other way around. The discriminator gets the image as input and should tell whether it's real or fake, right? Real or fake, you can see it as a binary. It's very small. So it's a small. Okay? So far clear? So the discriminator gives us some probability between 0 and 1, whether something is real or fake, right? Now, how can we model it mathematically? So far, good. Yashovenja says, well done, good fellow. Let's write it mathematically. So let's define this cost function. Expectation of logarithm of dx. By the way, don't panic when you see expectation. You can always approximate expectation by average. This is called Monte Carlo approximation. Okay. When you have some samples, you take average of this quantity with this across those samples, that you can approximate expectation. Of course, the larger the sample size, the more data points you have, the more accurate this Monte Carlo approximation is. Okay. So now I have this expectation of logarithm of dx. Dx is the output of discriminator, right? So as you see, we are maximizing. This is a minimax problem. You are maximizing this cost with respect to D discriminator and minimizing with respect to G. So the generator wants to minimize this equation 3. The discriminator wants to maximize it. They are enemies of each other, right? So now you tell me, maximizing this, what does it do? So the first term maximizing it. So it means that for real data, do you see expectation is over real data? For real data, I want this d of x, by the way, d of x is between 0 and 1. Do you remember? I told you. It gives us the probability, right? When I maximize log of d of x, logarithm is a monotonic function. So I'm maximizing d of x. Agree? So far clear? So when I maximize d of x for real data, what does it mean? I want a discriminator to output 1 or value close to 1 for real data. Now I think you can guess. It should give 0 or close to 0 for fake data, right? So this term is maximized, makes sense, I told you. The second term also has d in it. Let's see what it means. The second term has g of z, the latent noise, feed it to generator, gives you g of z, then the output of generator, which is some image, fake image, right? Fake image. You feed it to the discriminator. of course, the discriminator wants to output 0 for it, right? So the discriminator wants to minimize d of g of z, right? As a result, the discriminator wants to maximize 1 minus d of g of z. Minimizing d of g of z, sorry, that's minimizing d of g of z is equivalent to maximizing minus d of g of z, or maximizing 1 minus d of g of z, right? So the discriminator wants to maximize this. Logarithm is a monotonic function, so we can say it wants to maximize logarithm of 1 minus d of g of z. And expectation is over fake data, of course. So this also makes sense to maximize for discriminator. We talked about maximization of both terms for the discriminator. Now let's talk about minimization of this cost with respect to g. Okay. The first term, minimization of the first term with respect to g, what happens? Does the first term have g in it? So it's a constant, goes away. Constant in derivative becomes 0, right? The second term has g in it, right? Then I said that discriminator wants to output 0 for fake data, right? The second term is for fake data. So the generator wants to fool the discriminator. The generator wants to fool the discriminator. So the generator wants the discriminator to output 1 for fake data, right? So in other words, the generator wants d of g of z to be maximized, to become close to 1, right? So maximize d of g of z is equivalent to minimize minus d of g of z, or minimize 1 minus d of g of z, or minimize logarithm of 1 minus d of g of z, or minimize the whole second term. This makes sense to minimize. Did you see the beauty? This is how they designed this last function and interpreted that as a zero-sum two-player game. Interest. For more information on GAN, you can see our tutorial paper. I have a tutorial paper, very long, about GAN. This was the vanilla GAN, one of the original GAN. There are variants of GAN. Where a lot of variants of GAN, you can see a survey or a tutorial of that in our tutorial paper, available in archive. Also, some part of it has been published in our book. Okay, some slides of this slide deck are inspired by teachings of Professor Stanko Dimitrov at the University of Waterloo, and also based on the book Eric Rasmussen, Games and Information, an Introduction to Game Theory. By the way, I forgot that the game theory part is also inspired by teachings of Professor Algo at the University of Waterloo, the GAN part. For more information on GAN, see our tutorial paper, as I told you. And these are the references. This is the tutorial paper, Generative Adversarial Networks and Adversarial Autoencoders, tutorial and survey. By the way, this was Generative Adversarial Network. We also have Adversarial Autoencoders. And who was the main contributor for Adversarial Autoencoders? Do you know him? Alireza Makhzani. He's in University of Toronto. He recently has become an assistant professor in University of Toronto, and he's a Vector affiliate as well. Okay. By the way, I emailed him for postdoc. He never answered me back. Okay. So, any question? No? No? I think, so game theory is over, but I think we don't have enough time to go over right now, to go over reinforcement learning. But in the next session, we'll talk about fundamentals of reinforcement learning. We have 3 more sessions. Am I right? So yeah, in these 3 sessions, I think I can cover both RL and fuzzy logic. Let's see how it goes. Let's see. Okay. Okay. Thank you. Thank you.